Hello class, today we're going to go over 11.3, it's the integral test and estimates of sums. So the integral test, basically what it's telling us is if we have a sum, we can take the integral, and if the integral comes out to a value, a specific number, then our sum of our sequence is going to be also convergent. If the integral is divergent, then the sum of the series is going to be divergent. So that's the integral test. So let me show that to you so you can just see how it works. So in this example here, the function that we have is, and I'll just write it as f of x is equal to 1 over x squared plus 1. Right? We know that this function is continuous. It's positive, and it's decreasing. Those are part of the conditions that are needed, right, for the test. Continuous, positive, and decreasing function. This one has that, and it's going to be in that interval from 1 to infinity, right? We can put 1 in. It's defined that. It's within its domain, so that's continuous. It's definitely positive because of the squared term, and we see that it is going to be decreasing, and you could see that if you were to graph it going from 1 to infinity. Alright, now what we can do with this problem with the integral test is we can take the integral of it and we'll go from 1 to infinity of 1 over x squared plus 1 dx. But since we're going to infinity, we can't do an integral to infinity. We don't do it that way, so we're going to take the limit as t goes to infinity from 1 to t of 1 over x squared plus 1 dx. What's going to end up happening there is I'm going to get the limit as t goes to infinity of what's the integral of 1 over x squared plus 1. We should all know that now. It's the inverse of x evaluated from 1 to t. And so that's going to give me the limit as t goes to infinity of tan inverse of t minus tan inverse of 1, right? This is going to be, as t goes to infinity, that first one's going to be pi over 2, and the other one is going to be pi over 4, and so we see that our answer should be pi over 4 here. How did I know that it was pi over 2? If I look at the graph of tangent, it looks like this, right? And so as the value goes to positive infinity, I'm going to get pi over 2. So it's understanding limits, going back to chapter 2 of Calc 1 to get that. And then tan inverse of 1, we know to be pi over 4 from trigonometry, right? So that's the integral test right there. But these conditions need to hold true. It's got to be continuous, positive, and decreasing. All right, let me show you another one. And this one says that for what values of p is the series, the sum from 1 to infinity of 1 over np convergent? And so one of the things we can do is we can talk about it a little bit. So if p is less than 0, we know that the limit as n goes to infinity of 1 over n to the p is going to take off to infinity, right? Because any p value that we put in there is going to move it. If it's smaller than 0, meaning negative, is going to move the n up to the numerator, and so that going to infinity is going to take off to infinity. Obviously, it's infinity. If p is equal to 0, then the limit as n goes to infinity of 1 over n to the p is simply going to be 1, right? Because we're going to get the p to be 0, and so any number, it's going to be 1 as the value, right? So that's not too bad. What we need to run into an issue is we need to look at if p is greater than 0, then what happens is our f of x function becomes 1 over x to the p, and we know that this is going to be clearly continuous. It's going to be positive, right? And it's going to be decreasing. It's going to hold the 3 conditions that we need from 1 to infinity. So then from here we need to do the integral test to it, and we'll go from 1 to infinity of 1 over x to p dx. And what we see here is the integral of this is going to converge if p is greater than 1, and it diverges if p is less than or equal to 1. So it's pretty cool, the information that we're able to find from this. There's a dichotomy that happens in this problem, and so you need to understand the evaluating piece between being greater than 1 and being less than or equal to 1, very similar to the geometric series, right? So it ends up being a theorem, and this is the theorem. So if we have a p series, what ends up happening is if we're greater than 1, it's going to be convergent, and if it's less than or equal to 1, it'll be divergent. So let me show you this and use it in a very practical sense so you guys can actually understand how simple it is. In this example here that we have, the p clearly is 3, right? And since our p in this problem is 3, p equals 3, that's bigger than 1. What that tells me is that this must converge. And so since it converges, that means that it's going to go to some value that we can find. Cool, not bad, right? In this one, our p value is 1/3. So if p equals 1/3, that's less than or equal to 1. And so what does it tell us? That this is going to diverge. And so when we see this value, we know it's going to take off to take off without bound, right? So that's what's going to happen with the p-value there. All right. Now the next thing that we have is the remainder estimate for the integral test. So what's going on here is the remainder ends up being the difference of the it's the sum minus the sum of the nth terms, right? And so what we end up seeing is that the remainder ends up falling in between the integral of the function going from these two values here. I'll demonstrate that for you, so don't worry. Here's an example so you can see. All right, so in this problem, we're going to actually do some pretty cool stuff. We're starting to do some analysis, which is kind of fun. In this problem, we're going to approximate the sum of the example where we said it was convergent, right? And we're going to find the first 10 terms, and then we're going to try to see if we can estimate what the error is, how far off we are going to be. So remember, we're going to go from our n to infinity of 1 over x cubed dx. So that's going to be the limit as t goes to 0, or t goes to infinity, of a negative 1 over 2x squared from n to t, right? That's just doing the integral piece that we did, going from n to infinity and then changing the infinity to t. So that's how we got that. And then we're going to get the limit as t goes to infinity of a negative 1 over 2t squared plus 1 over 2n squared. And then when we apply the infinity, we see that the first is going to go to 0. So we're going to get 1 over 2 to the n squared. Right? Now, what we can do to find the sum of this thing, we can do that quite simply by going the sum infinity of n equals 1 of 1 over n cubed is going to be approximately the sum of the 10. That's what we're going after, which is 1 over 1 to the third plus 1 over 2 to the third plus 1 over 3 to the third to 1 over 10 to the third, which is going to be approximately 1.1975. And now we want to find out what the error is. And so the error that we're going to find is going to be this. So our remainder is going to be less than or equal to the integral from 10 to infinity of 1 over x to the third dx, right? Because there's 10 terms. That's where we start with our n. And we know that the integral was 1 over 2, and then our n was now 10. And so we get 1 over 200 as our error size. So the size of the error is at most 0.005. And so this here, what I did here, this is what's providing us with the error for our problem. And then I found what this is the solution, our approximate solution, and we might be off, or we will be off by something within 0.005 or 5 thousandths of the increment measure, which is pretty cool. Now, for part B, it says how many terms are required for us to add up to get an accuracy of 5 10,000ths, right? Tens, hundreds, thousands, 10,000ths, yeah. So here's how we do that. We're going to want our remainder to be less than 0.000, right? 305. And so we're going to say, okay, r sub n has to be less than or equal to, or less than, n to infinity of 1 over x to the third dx. But we know that that's 1 over 2n squared, right? Because we did the integral piece up here to find out what our error would be, or remainder would be. And so then from here what we're going to say is, okay, then 1 over 2n squared has to be less than 0.0005. If I multiply by 2, I'm going to get 0.001. And then I'm going to go 1 divided by 0.001 is less than n squared. Correct? And so then n is going to be, I should write it this way, n squared is about 1,000, right? It's going to be greater than 1,000, so n then is going to be greater than the root of 1,000, and the root of 1,000 is 31.6 approximately, right? And so to be accurate, we can't do 31 terms. That would be not big enough. We have to always round up. So that tells us that we need 32. Ooh, I need to be able to write 32 terms to be at a right accuracy to within 0.0005 of our recommended error. This is 11.3. It's really not bad. What I'm going to try to do going forward, just so you all know, I'm going to do all our lessons asynchronously, going the rest of the way, so you can work at them at your own pace. And then what I want to do during class time is just answer questions on homework and work with you guys through the homework so that you guys better understand it and are successful in doing it. All right? I hope this finds you well. I'll see you soon. Bye-bye.